Here we have an example of a Cauchy Euler equation, second order differential equation, and it's basically a linear homogeneous differential equation with variable coefficients. So the coefficients on a normal differential equations, second order, wouldn't have a variable here, would have a number, a number, and a number. But here we have variables x squared, variables x. And this exact example was actually taken from a challenge question from Further Maths Pure 2 book and sent to me by one of my students. So I'm going to have a go at doing this for my students as well as whoever find this topic interesting. So the suggestion here is to use a substitution of x equal to e to the power of u. And so we're going to use this substitution, and we're going to change this differential equation into a one that has got no variable coefficient, one that we know how to deal with. So if I start by this substitution, so this will tell me straight away that log natural of x is equal to u. And so if I differentiate both sides of this, I would get du dx, and the differential of a log natural of x would be 1 over x, which again I can replace this x with this, so it would be 1 over e to the power of u, or in fact simply written as e to the power of minus u. So the direction that we're going to take is to see if we can change the variable dx to u. So I start with the first differential of y with respect to x. This is what we normally know as dy dx. And this could be the variable of this differential can be changed to dy to du as long as we multiply this by a du dx. So in a sense, what I am saying is that dy dx, which is the first differential of y, is actually equal to dy du multiplied by du dx, and this du dx we already know from here. We know that du dx is in fact e to the power of minus u. So we're going to take a note of this later on. So we're going to use this first differential equation later on. And let's now find the second differential equation. So the second differential equation, which we normally write it as d2y dx squared, is in fact the differential of, with respect to x, is the differential of the first differential, which is dy dx. Now, if I want to change the variable of this differentiation, I would take the differential of dy dx with respect to du, as long as I multiply this by the chain du dx. So in a sense, what we really have to do is to differentiate. So we're going to differentiate with respect to u. We're going to differentiate the first differential, which is here. That's the first differential. So we're going to write that in there. So that's dy du e to the power of minus u. And as long as we multiply it by the chain of du dx, which in fact is this. So I'm just going to write that as e to the power of minus u. So really, the second differential. Let's move up a little bit. So really, the second differential, d2y dx squared, is in fact, slice it a bit neater. So is in fact the differential with respect to u of this product. So it'll be the differential of that multiplied by the second part, the differential of the second part multiplied by the first part. So this is a product to be differentiated, and that outside. So we will have the differential of dy du, which would be the second dy du squared multiplied by the first part, which is this, and then minus, because the differential of e to the power of minus u with respect to u would be minus, and multiplying it by the first part, which would be dy du, and then e to the power of minus u. And then outside of this, we will have e to the power of minus u. So if I if I just finish this off and simplify it, I want to keep both of these in view. So I'll try and keep both of these in view. So we'll have the second differential d2y dx squared, which in fact we found in terms of du to be equal to d2y du squared e to the power of some. I'm basically multiplying this in, yeah. So when I multiply that in, I will get e to the power of minus 2u, and then minus dy du e to the power of minus 2u. So this is our second differential. So let's make a copy of our first differential, put them next to one another. Make a copy of that and put it here. And also maybe we take a note of the original function. So I'll bring that down here and put it next to these. I'll put it here. And then so now we are going to substitute, and hopefully by substituting we'll be able to get rid of dy dx, and in exchange we will have dy du. So I have so in the original we have x squared. Well, x squared would be, well, we know that x was actually substituted with e to the power of u. Yeah. So by substituting, we will have e to the power of 2u, so that's x squared, and then we'll multiply it by the second differential. Well, the second differential is here. This is the second differential. So if we multiply it, we would have d2y du squared e to the power of minus 2u minus dy du e to the power of minus 2u. So that's the first part of the substitution done. So we've done this bit now. So we're going to do 4x. Well, x is e to the power of u. So 4 of that multiplied by the first differential. So it'll be plus 4 e to the power of u, and then multiplied by the first differential. And the first differential is this. So it would be dy du e to the power of minus u, and then we would have plus 2y equal log natural of x. Not log natural of x, we showed at the top that it was actually equal to u. So it would be plus 2y equals u. Well, that's very much easy to simplify. So really what we do is we'll multiply this in. So as we multiply this in and this in, we will end up with d2y du squared. Let's write this a bit nicer. So d2y du squared, and then when I multiply by the second part, it would be dy du. So that's simplified. Now we're going to take that in there. So you would get plus 4 dy du, and then plus 2y is equal to u. Let's take one more step to simplify. So it'll be d2y du squared. These two will add together, and that would give you plus 3 dy du plus 2y is equal to u. That's in a standard second order differential equation, but of course it's in terms of u. It's no longer in terms of x. So if we now go for finding the auxiliary function, the auxiliary equation would be m squared plus 3m plus 2 is equal to 0, which will factorize to m plus 1 and m plus 2 is equal to 0. And that will give you two m's. It will give you m equals to minus 1 and m equals to minus 2. So our complementary function will be y is equal to a e to the power of minus 1 u, variable here is u, plus b e to the power of minus 2u. Yeah. Okay. Now I'm going to make a copy of this, because in a minute I will be using this again to find my particular. Put it here. We'll be using it to find our particular integral. So let's just make a little box around it. So the particular integral, I'll just write it on the side here. The particular integral can, because on the other side we just have a u. It's just one single of order 1 variable. So so the particular integral can be y is equal to lambda u, so is a linear function. So lambda u plus mu. So if I integrate, sorry, if I differentiate this, the first order differential of that would just be lambda, and the second one will just be 0. So if we substitute this back into here, we can find what lambda and mu should be. So let's just go ahead and substitute in there. So so that's 0. So let's forget about that one. Then we got 3 of the first differential, which is this. So 3 lambda, and then 2y, which is double of that. So that will be plus 2 lambda u plus 2 mu. And that has to be equal to just u. So that's just 1 u. Yeah. Okay, so let's equate the equal parameters here. So you will have that is like term with that. So therefore 2 lambda must be equal to 1. And since the other side doesn't have a constant, so no, so therefore 3 lambda plus 2 mu must be equal to 0. So from here we conclude that lambda is equal to 1/2, and then from here 3 halves plus 2 mu is equal to 0, which will conclude that mu would be equal to minus 3/4. So the complete function in terms of u is a e to the power of minus 1u plus b e to the power of minus 2u, and then plus the particular function, which was lambda u, so that would be 1/2 of u, and then minus and then the mu, which was minus 3/4. Now, we so this is y in terms of u, but of course the question was a differential equation relating y. It was relating y to x, so we need to just replace that back in. So wherever I see u, I'm going to place log natural. So here we would have y is equal to a e to the power of minus log natural of x plus b e to the power of minus 2 log natural of x, and then plus half log natural of x minus 3/4. And so, as you know, we can take these powers in, so that would be x to the power of minus 1, x to the power of minus 2. So in fact y would be equal to a e to the power of log natural of 1 over x plus b e to the power of log natural of 1 over x squared plus half of log natural of x minus 3/4. We can simplify this a little bit further, because the e to the power of log natural of x will just simplify to 1 over x. So in effect, the final version would be y is equal to a over x plus b over x squared plus we can write this as log natural of square root of x minus 3/4. Now the other part of the question, so if I can bring the question in again, the other part is not really that challenging now. So if we bring it in, it just says find the equation of the solution curve passing through the point 1 and 1. So basically that is telling me that when x is 1, y is 1. So if we just have a look at what we have here, we're saying that 1 is equal to a over 1 plus b over 1 plus log natural of that, which is 0, minus 3/4. So that simplifies to, I'll just write it here, that simplifies to 1 3/4 is equal to a plus b. And then the differential of it, so the gradient is differential. So the differential of it is 1. So that we go back to, if we go back to here and we differentiate this, we will have dy dx. So dy dx would be equal to minus a over x squared, and then minus 2b x cubed, and it would be so if that's half x, if that's half of log natural of x, it would be 1 over 2x, and so therefore gradient is also 1. So if we replace this, so 1 is equal to, and x is 1, so it'll be minus a minus 2b plus a half, and that will give me an equation. So that was my first equation. So that gives me also another equation, which would be, so I'll take the half to the other side. So it'll be a half is equal to minus a minus 2b. And of course, this is not a difficult thing to do. So you can just solve these as simultaneous equation, and that will give you the a and b. So if you just add these together, if you add these two equations together, the a and the a will cancel each other out, and you would have 1 3/4 plus a 2/4 So you will have 1 3/4 plus a half, which would be equal to minus b. Yeah. So 1 3/4 is 7/4 plus 2/4 equals to minus b, which means that 9/4 is equal to minus b, or b is equal to minus 9/4. Yeah, and then you can go and find a. So really, this part isn't that hard to finish. Okay.